In this video, let us see what is hysteresis in magnetism. To magnetize a material or a specimen, it is to be kept in a magnetic field. Then because of the current through this coil, there is a magnetizing field. So let it be H. Then magnetism will be induced in the specimen. So magnetic induction, let it be B. In the case of ferromagnetic materials, B by H is not a constant. We can draw a graph by taking magnetizing field along the x-axis, here plus H, minus H. Then magnetic induction is marked along the y-axis, plus B, minus B. Here you can see it is not a straight line. As H increases, B is also increasing, but it's not a linear relation. So this is the graph. From A, you go on increasing the magnetizing field. H is increasing, B is also increasing. Finally, it is becoming a constant. It is attaining a saturation value. Then you go on decreasing the magnetizing field. Then it is not retracing the same path. When you are increasing the magnetizing field, magnetic induction is following this path, AC. It is, as H increases, B also increases and it becomes constant. It attains saturation value. Now you decrease H. It is not retracing the path and coming back to the same point A, but it is following this path, CT. So now H has become 0. And H has become 0, but B has not become 0. So this much residual magnetism. This AD is residual magnetism. So H has become 0, but B has not become 0. Now you reverse the magnetizing field. Then increase the magnetic field in the reverse direction. So you can see now B is going on decreasing and finally B has become 0. B is becoming 0 at the point E. So this much negative field is reverse field is to be applied to make the magnetism, residual magnetism to be 0. So that reverse field is called coercivity. AE is called coercivity. Next, again you go on increasing the magnetizing field in the reverse direction. So you can see that B is going on increasing in the reverse direction. Then it has become maximum, that is saturation value. It is attaining saturation value. Next, you decrease the magnetizing field. Then again you reverse the direction and increase the magnetizing field. So it will follow the path F, G, K, C and coming back to the point C. So this is called hysteresis loop. Now this closed loop A, C, D, E, F, G, K, C. A, C, D, E, F, G, K, C. This closed loop is what's called hysteresis loop. Here you have seen that when H is becoming 0, D has not become 0. So there is a lagging of magnetic induction behind the magnetizing field. That is what's called hysteresis. Hysteresis is the phenomena in which there is a lagging of magnetic induction behind the magnetizing field. Now here AD and AG are known as residual magnetism. Residual magnetism is also known as remnants or retentivity, is the ability of the material to retain the magnetism even when magnetizing field vanishes. Here magnetic field has vanished, but this much magnetism is retained. That's why AD is residual. AD and AG, residual magnetism. AE and AK are coercivity. Coercivity is the reverse magnetic field to be applied to make the residual magnetism zero. That is what's called coercivity. When a specimen is magnetized through a cycle, there is a loss of energy in the form of heat. That is due to the rotation or orientation of molecular magnets in the specimen. Energy is lost in the form of heat. Energy lost per unit volume of the specimen is given by the area of the loop. So that is integral of H dot dB vector. So when you integrate this, you will get the area of this loop. So area of the loop will give you the energy lost per unit volume. Based on the shape and size of the hysteresis loop, ferromagnetic materials can be divided into two: soft magnetic materials and hard magnetic materials. Soft magnetic materials, area of the hysteresis loop is less, and hard magnetic materials, area of the hysteresis loop is large. Then for soft magnetic materials, retentivity is less compared to hard magnetic materials. Hard magnetic materials, retentivity is more than for soft magnetic materials, retentivity is less. Then coercivity is less for soft magnetic materials, and for hard magnetic materials, coercivity is more. But susceptibility is more for soft magnetic materials. That means soft magnetic materials can be easily magnetized. So example for soft magnetic materials: soft iron, mu metal, and stelloid. Then for hard magnetic materials: steel, alnico, and lodestone. So this graph is for silicon steel. So it's a soft magnetic material. This graph is for carbon steel. Soft iron can be easily magnetized, but when the external field is removed, magnetism disappears. So for soft magnetic materials, when the external magnetic field is removed, magnetism disappears. And thank you for watching.